Welcome. Thanks for tuning into our virtual demo. I'm Vincent Liuzzi, a field applications engineer at Multilane, and I'm here to show you how you can leverage Multilane instruments to do 400 gig and 800 gig switch testing. With 400 gig hosts already out and 800 gig right around the corner, it is more important than ever to understand your host's response to crosstalk interference. The Multilane EN BERT family's unique shallow loopback and noise injection feature enables you to take an input signal to the BERT, inject noise onto that signal, and output it for analysis and measurement. This analysis can be done on a network host, an eval board, or anything else that you can connect the BERT to. Today, we're going to use the shallow loopback and noise injection features to test the crosstalk interference response of a switch. So let me go over the setup that we're going to use. So what we're going to do is we're going to take this 400 gig Accton switch, and we're going to take a clean electrical signal out of it, and we're going to connect it to our BERT. And we're going to use the shallow loopback feature to loop back that signal. But before we do that, we're going to use the noise injection feature to inject noise onto that signal to emulate crosstalk interference, and then we'll send that stress signal back to the switch where we will do both BER and FEC testing. Now before I get into the testing, I want to show you the specific hardware that we're going to use for this setup. First, we have the 400 gig QSFP DD Accton switch. Plugged into one of those ports, we have the MO4062BO, which is a host compliance board breakout for QSFP DD. Then we have this cabled to two 4039EN BERTs. Each of these BERTs is 4 channels, so we're going to need 2 of them to do 8x50, which is 400 gig electrical. Instead of using two 4039ENs, you can also use a 4079EN, which is Multilane's new 8-channel 800 gig BERT, which is going to be released in early 2021. As that's not quite released yet, today for this demo, we'll be using two 4039ENs. As you can hear from the lack of loud noise, the switch is not on yet. So I'm going to turn on the switch, and then we'll head over to the switch's diagnostic command line, and we'll start some testing. Okay, so now we're at the switch console. In addition to having the switch console to control the switch, I have 2 of the BERTs on the new Thunderbird GUI. If you're unfamiliar with Multilane's new Thunderbird GUI, my colleague Hanny Dow does a great demo on this. You should watch that. We're not going to get into specifically how to use the Thunderbird GUI or all its great features. We're specifically going to go over 2 of them. The first is the shallow loopback feature. This is the feature that we're going to use today, and you can see that it's on because it's lit up green. I can turn it off, it's gray. Turn it back on, we get the green, shallow loopback is on. And the other is noise injection. Right now, noise is enabled. In order to set the noise, I have to go to the TX for each channel. So I'll start with the first channel, and you can see that green ends, so you can tell that the noise is on for all 4 of these channels. And I'm going to click it, and you can see down here noise injection. Right now, we have the pattern on random noise, and we have the noise level on 500. So for noise level, actually, we've implemented noise in Thunderbird with a unitless digital scale to simplify the application. The Thunderbird API provides use with more granular control over the line rate and pattern of the noise source, but today we're going to be using the GUI for simplicity, and we're going to use random noise to emulate the crosstalk. So this unitless scale goes from -1000 to 1000, with 0 being no noise. So I've set every single channel to 500 units of noise, which is about half. And we're going to go from there and see what the BER and the FEC statistics look like with that much noise injected onto the channels. So the first thing we want to do on the switch is set the traffic to be PRBS 31 traffic, which is what we're using on the BERTs. So that's what I'm going to do with this command here. And I need to set it for port 16, because that is the port we are going to be using that I have plugged into the switch. Instantly, when I set that PRBS traffic, you can see the green locks on the RXs go up on both BERTs. This means that we have locked to the PRBS 31 pattern, and now we can do BER tests. So I'm going to start a BER test very quickly, and we will see what the BER looks like. Now, the important reason for testing BER and FEC statistics here is with 400 gig and 800 gig PAM4 signals, they can be very sensitive to crosstalk noise. And so we're going to test and see, as we increase that noise, emulate crosstalk noise, what happens to the BER. So this command right here is going to start, and I'm going to set the interval for 10 seconds, a PRBS statistics test, which is where we can get the BER. So 10-second interval. So after 10 seconds, we get the BER. And we look, and most of these are around 1E, 1E minus 9, minus 10 for the BER, which is not great, but also not too terrible. And that's because of the noise. So before, and to save us some time from doing all the different noise levels, beforehand, I actually did a test where I ran 3 1-minute tests of BER for each noise value in increments of 100 up to 1,000. And here's the data that we got. As you can see, at 0 noise and at 300, up to around 300 noise, we got about E minus 12 BER. But around 300 noise is where the switch stopped being able to filter out the noise injection, and we started to get a lot more errors. And up at 1,000 noise, we even got E to the minus 4 BER, which is really, really bad. What you can really see from this test is how the switch responds to this noise injection or this crosstalk emulation. At a certain point, which is about 300 units of noise here, 400 units of noise, it starts to be too much for the switch to filter out, and we start to see the crosstalk emulation, the noise, have a pretty bad effect on the BER. So now let's take a look at some FEC statistics. So we're going to go over and we're going to stop, first of all, stop this BER test. Then what we're going to do next is we're actually going to turn off PRBS pattern. And as we look over at our BERTs, we're going to see that we've lost lock on RX because there's still traffic coming through, but it's not PRBS pattern traffic. And it's still looping that traffic back. And the way you can see that is we're going to look at the port status. And as you can see, port 16, which is the one we're using, even though we don't have a PRBS set, we're not seeing lock over here, it's still looping back the signal. And you can see that because the link is up. You can see the link up for port 16. So now we'll run some FEC statistics. So the FEC statistics test allows you to see the counters of the corrected and uncorrected code words. I'm going to start this test for the same as the other one, another 10 seconds, and we'll take a look at what the results are. Just to verify, I looked at the pre-FEC BER using FEC statistics to make sure it was similar to what we were seeing beforehand. And we're actually seeing that. We're seeing about 2.8 e to the minus 9, which is about what we saw on the BER test. So we'll take a look at the counters. And in these 10 seconds, we got 24,000 corrected code words and 0 uncorrected code words. This means that FEC was able to handle that and correct all the code words, which is good to see. But I did a test beforehand testing every single level. In this test, I actually did an average of 5 1-minute tests at each noise level in increments of 100 units of noise. And here we can see the corrected and uncorrected code words versus this injected noise. So we actually see a similar trend as we see on the BER graph. Up until about 300 injected units of noise, we see relatively low corrected code words, and we see the traffic being very good, and then it starts to taper off and get worse and worse and worse. And here we even see at 1,000 units of noise, we see about, maybe 100, between 100 and 1,000 uncorrected code words, which means FEC is failing at this point. And in a similar story, you can see how the switch's response to this crosstalk injected noises. It starts to fail at a certain point, and this is how you can test your host. And the exciting thing about this is really the EN BERT family, whether it's 239 ENs or one of the 4079 ENs, which is coming out in early 2021, is a one-stop shop for 400 gig and 800 gig host testing, because these BERTs are capable of both 26 gigabaud, which is 400 gig, or 53 gigabaud, which is 800 gig. And this is great because whether you're ramping up with 400 gig hosts or still, pushing to develop your new 800 gig hosts, this is an exciting way to analyze the crosstalk responsivity of your host. Thanks for tuning in to this demo. If you have any questions or concerns, please contact us at fae@multilaneinc.com. And please take time to listen to our other demos, and thank you.